Clairaut's theorem may come in handy from time to time. And this is what the theorem says. Basically, it says, suppose f is defined on a disk D that contains a point AB. If the functions, the partials of respect to x and then y, and fyx, the partials of y, then with respect to x, are both continuous, they both need to be continuous on D, on that disk, then fxy at AB equal to fxy or yx at AB. So what we saw in the previous example where we end up with a situation where we found this to be true, that was because we have these necessary conditions. Now in the previous example, we had f of x y was equal to x e to the yx. Notice this is continuous everywhere. And then the partial derivatives, fx was e y to the x plus yx e to the yx, and you may or may not have factored that out, but that's okay. There it is. And you notice this is continuous everywhere. So if it's continuous everywhere, clearly it's going to be continuous in any disk D about the point AB. And the partial with respect to y was x squared e to the yx, which is also continuous everywhere. So the conditions for Clairaut's theorem have been satisfied. So based on that, we know going into this that the partial with respect to of x and then to y is going to be equal to the partial with respect to y and then to x, evaluated at this point. And because it's continuous everywhere, all these functions are in fact continuous everywhere, it's not just some region about AB, then that's going to be true for any AB that are both real numbers. So for this function, we know that Clairaut's theorem does apply, as in the previous example we showed that it did.